Today we're going to be looking at solving exponential equations. Remember that in our last lesson we looked at graphing exponential functions. And our equations are going to be very similar, meaning that we're looking at equations with the variable in the exponent. So the example, or what we're going to need to be using, are our exponential property of equality. And because our exponent is where our variable is, we're going to have to look at it a little bit differently. So notice that we have b to the x equals b to the y. Well, since our bases are the same, the only way for the left side to equal the right side is if our exponents are also the same, which means that x has to equal y. So the example that they give is if I have 3 to the x and it equals 3 to the fifth, notice that my 3's are the same, and that's not going to change. So in order for the left side to then equal the right side, my exponents must also be equal, which in this case would mean x has to equal 5. So we've solved for our variable. So let's look at an example. In this case, we have 2 to the x equals 8 to the third. Now this is a little bit different than the example that we just saw, because notice that our bases are different. We have a 2 and we have an 8. So we can't just set our exponents equal to each other. However, we can think about, okay, using my exponent rules that we've learned, is there a way that we can rewrite our bases to be the same? And one way of doing that is looking at each of our numbers. So notice that there's no way for us to rewrite 2 because it's a prime number. However, we can rewrite 8 as 2 to the third. And then we also still have that other third power on the outside. Then, using our exponent properties, we know raising a power to another power, we multiply those powers. So 3 times 3 gives us 9. Well, now that since my bases are the same, I have 2's for both of them, we can say, well, then I'm able to just look at my exponents. So x has to equal 9. And we've solved for x. Looking at our next example, this time we have a 3 and a 9. So again, our bases aren't the same, but we need to think about, is there a way that we could use our exponent rules so that we could make them the same? And hopefully that we notice that 9 is going to equal 3 squared. And then that 2x minus 1 is still on the outside of our exponent. And again, remember, when we raise a power to another power, we're going to multiply. So now my bases are the same. I have 3's for both of those, so I can set the exponents equal to each other. And at this point, we just have a multi-step equation that we've seen since we were in pre-algebra. So my first step is to distribute the 2. Then we want to move all of our x's to the same side, and finally divide by 2. So we get that x equals -1. On our next one, we have a 4 and we have a 64. So again, we're looking at, is there a way that I can rewrite 4 to have the same base as 64, or 64 to have the same base as 4? And the good rule of thumb is we're always going to rewrite the bigger one. Now, sometimes we might have to rewrite both of them, but you will never just rewrite your smaller base. So in this case, we can rewrite our 64 as 4 to the third. Again, once we have our bases the same, we can just set our exponents equal to each other. So we get 2n equals 4, so n equals 2. Then we have 5 to of 5x equals 125. Well, 125 is going to be 5 to the third, and then we still have our x plus 2 there. Again, be careful because when we raise that power to another power, we need to multiply it, but we have to multiply it to the whole thing. We can't just put the 3 in front of the x and forget about the 2, because we have to distribute that 3 whenever we start solving. So because my 5's are the same, we can go ahead and write our exponents equal to each other. And then we'll just solve from there. And we get that x equals 3. Now, like I said, there might be some instances where we have to rewrite both of our bases. So if we had something like 4 to the x equals 8 squared, well, notice that I can't write 8, which is my bigger base, as something with a 4. I can rewrite it as 4 times 2, but that's not with exponents, and we have to use exponents when we're rewriting. But notice that we could rewrite both of these with a base of 2. So we would have 2 squared and 2 to the third. So we end up with 2 to the 2x equals 2 to the 6th. So 2x equals 6. So x has to equal 3. So that's just something to keep in mind, that every once in a while you might have to rewrite both of your bases and not just one of them. So let's look at another example. This is a real-world application problem. So bacteria growth is a very good example of something that's going to use an exponential function to model what the situation is going to look like. So whenever we're using a model, we want to use our y equals a to the bx power. And that's going to be our basis of our exponential function. So in this case, they say Kristen starts an experiment with 7,500 bacteria cells. After 4 hours, there are 23,000 cells. Write an exponential function that could be used to model the number of bacteria after x hours if the number of bacteria changes at the same rate. Now that part at the end there where it says changes at the same rate is important because that tells us that our base is going to be consistent. And they also ask us to use an exponential function. So we know that our x has to be in the exponent. From there, because they ask us to write a function, we want to leave our y and our x there in our final answer. But right now, we need to solve for that a and our b. So in the meantime, we might have to plug things in for our x and our y to be able to solve for a and b. But remember, in the end, we want our final answer to still have x and y in them. So a big thing is that they tell us that our x represents time, which makes sense because remember that time is going to be our independent variable, which is what x is as well. What that means then is that our y, which is our dependent variable, is going to represent our population. So like I said, they give us some information to start out with, and we need to use that information. So they tell us that at the beginning of the experiment, the population of bacteria is 7,500. Well, we said 7,500 is represented by y. So we plug that in to see if maybe we can solve for a or b. Now they say at the start of the experiment, which means that no time has passed, so our time at that time is going to be 0. Well, again, needing to use our exponent rules, anything to the 0 power is going to be 1. So then that would just be a times 1, which just gives us a. So we've solved for one of our variables. We still need to find our base or our b value. And so then that's when we're going to use the second piece of information that they give us. So they tell us that 23,000 cells, which again is our population, so we're going to put that in for our y value. We've already found our a value, so I'm going to go ahead and substitute that in for a. We're looking for our b value, so I'm going to continue to put my b there. And they tell us that we get that 23,000 after 4 hours, which is what's going to go in for our x. And then we just want to solve for b. And this should look vaguely familiar because this is the type of equations that we saw in the last chapter. So our first goal is going to be to get the b by itself. So we're going to need to divide by 7,500 to both sides. And we're going to go ahead and leave this as a fraction. So we would get 46 over 15, b to the fourth. Well, remember that we undo a fourth power by taking the fourth root of both sides. So we have the fourth root of 46 divided by 15. So we end up with 1.323 is approximately b. Now again, remember, we found a, we found b, but those aren't our final answers. Remember that they asked for our answer to be written as a function, which means that we need to plug both of those back in. So in order to have a function, I still need a y and I still need an x. So I'm going to leave those variables alone. So I'm going to have 7,500 times 1.323 to the x power. And that would be my final answer for that part of the question. My second part of the question asks us then, how many cells would we have after 12 hours? So we're going to go ahead and use that same function that we just found from the previous answer and plug in 12 for my time. Then we're going to plug all of that in to our handy dandy calculator. And we get y equals 215,000 664.863. Now, because this is a real-world application, we're going to go ahead and round to the nearest whole bacteria and put a unit on our answers, which in this case is going to be cells. And so that would be my final answer. Now, that's one way that we can see having to create an exponential function. The other way that we can see it is given 2 points, but the process is going to be very similar. Again, we're still going to be using that same base formula, which is that y equals a times b to the x. And last time they gave us things in time and population, and that represented our x and y. This time they're giving things to us as points, but remember that points still also equal our x and our y. So again, we're going to use those points to plug in, like our 6.4 for y and our 0 for x, in order to help us to solve. And again, anything to the 0 power is going to be 1, so we end up with 6.4 as our a. Then we're going to use that second point to go ahead and plug that in. We already found that our a value is 6.4. We're looking for our b value, and we're going to plug that x into our exponent. And so it's raised to the third power. Again, we need to solve for b, so we're going to get the base by itself. And then remember that we undo raising something to the third power by taking the third root. And again, plugging all of that into our calculator, what's nice is that this time we actually get 2.5 exactly. And again, remember that solving for my A and my B are steps in my process to find my answer, but they are not my final answer. Remember that my final answer needs to be rewritten as a function. So I'm going to plug those values back in. So I have 6.4 times 2.5 to the x power. And that would be my final answer. So we need to be able to solve these types of questions, whether they're given to us as a real-world application problem or if they're just given to us as points.